Hi, in this video, we'll be continuing the study of ODEs, and today we'll really talk about certain differences between linear and nonlinear equations. So, in the previous 3 videos, we have went through terminologies related to the linear ordinary differential equations, and we were able to solve certain differential equations that were separable or using the integrating factor. So, the question now is, how do we know that a solution even exists in the first place? Because if the solution doesn't exist, then we'll be wasting our time trying to use methods to try to solve it. And this leads us to an important theorem for linear ODEs, is that if your function earlier, so this is the simple version first, and we will build our understanding to move on to more complicated ones. But let's say that our linear ODE looks like the standard form, and the coefficients are continuous within an open interval containing the initial point. Then there will exist a unique function that satisfies this ODE. So what does that mean is that not only do we know that there is a solution, we know that that can only be the only solution for the ODE. So this theorem exerts both the existence and uniqueness of solution to the initial value problem that we've always done. So we just need, that is, the solution of this can be discontinuous or fail to exist when at least P or G is discontinuous. So this doesn't work when you know that P or G is discontinuous at a certain point. And the proof follows from just using the integrating factor. Because if you use the integrating factor, that can only be, it'll still be a solution. You used it to show that it is a solution. And not only that, it must be the only solution because you didn't change any of the solution space across every equality line. So this way of solving it just literally explicitly proves that there will be a unique solution. So if you look at the proof, it's really about just using the integrating factor and verifying that the expression still remains as the solution to the IVP or ODE. So let's just take a look at certain questions to see how do we use this uniqueness theorem. So if we're supposed to find the interval in which this IVP has a unique solution, we must first rewrite it in standard form, and what we realize is that G is continuous for all t because it's for t, but this P function is only continuous every point except 0. So because the initial point is lying on the right branch, so it must be t larger than 0. It's because it must contain the initial value point to have a solution there. So this problem has a unique solution from 0 to infinity. So you can see how we have used the theorem to help us find the interval in which there will be a solution. And we have earlier already showed that the solution to this IVP is the following form, where t is larger than 0. Now, if we suppose we change the initial condition to -1, then our branch will be the left branch now, because now t has to be less than 0. So we can then verify that the interval, even though the solution is again given by this equation, the interval now is t less than 0. So I can hope you can understand how does changing the initial value will change the domain of the solution in the end. So while we talk about how linear equations have unique solutions, now we have to go on to the nonlinear examples. And if you see what is a nonlinear example, a nonlinear example looks like the following form. So the dy dx equals to y squared instead of y to the power 1. So when it's y squared, now this is still a separable equation, so you can just use separable techniques to solve it. So separable just helps you solve first order differential equation. Integrating factor helps you solve first order linear differential equation. So this is 1 over y, and when you integrate it, in the end you'll get that y equals to 1 over y naught, which is the reciprocal of the initial, minus x. And thus the function is not defined on x equals to 1 over y naught. If y naught is larger than 0, then the solution exists in this interval, and if it's less than 0, then it exists in this interval. And you can see it from the direction field and integral curve. So you can see how that even though the coefficients of the terms are all continuous and well defined throughout the entire real plane, the solution will fail to exist in the entire interval. So why do I emphasize this? Because if you look back at the theorem, it says that whenever this and this have an interval that they are both continuous, then the solution lies in that same interval. So in this case now, even though the whole interval is used, but the solution fails to exist within this whole interval. So you can see how when it's a nonlinear ODE, you cannot use the theorem anymore, and it might go off tracks. Then this comes another form of the theorem, which is stronger, is that if we now have a function f and we know that its partial derivative with y is continuous in some rectangle, then in some interval within this rectangle, there will be a unique solution for the IVP of this ODE. So this means that this ODE may or may not be linear, but we still know that there will be a unique solution, but we might not be able to tell what is this interval that it has until solving it. So there will be some geometric consequence of the uniqueness part, such that the two graphs cannot intersect each other. Otherwise, the two solutions will satisfy the initial conditions, contradicting the uniqueness of the theorem. So everything is by 1-to-1. So observe that the hypothesis now reduces to the linear form when you have the following cases. So for the proof of theorem 2.4.1, which was earlier, the linear version only, it was simpler because we had an expression that we can use to verify the solution. But in this case now, because it's non-linear version, there will be no expression that we can use, as there will be no integrating factor in this case. And so for the proof of this theorem, existence and uniqueness of solutions, we will leave it to a separate video by itself, as we'll try to go in depth into the proof. And we need to build up some knowledge more first. So right now we'll just take examples to familiarize ourselves with nonlinear IVP problems. And one of them is the following. In this case, what we need to know is that we see that the function here is continuous and the partial derivative is also continuous except when the line is y equals to 1. Thus, we can draw an open rectangle about 0 to minus 1, which is the initial value on which f and the partial derivative are both continuous as long as it doesn't overlap with y equals to 1. And this will give, and we'll now know that based on the theorem earlier above, we will have a unique solution about this interval. Another example of a nonlinear IVP is the following. And in this case, we know that f is continuous everywhere, but the partial derivative doesn't exist when y equals to 0. Hence, this theorem is not satisfied because the initial value is at 0. So in whatever interval we will have to whatever interval about 0 we have to contain, we will have an interval near it such that this partial derivative will not be continuous, will not even exist. And with that, because it's not satisfied, the solutions exist, but because we can show that the solution exists by variable separable methods. But in this case now, we get that the solution is no longer unique. That's why this is how we can actually see that the theorem fails. But if we were able to have an initial condition that is not on the t-axis, then we can indeed guarantee that there will be a unique and solution. And so this leads us to the next definition, and it's called the interval of definition. And that's basically the interval for which t lies such that the solution for the IVP is unique and exists. So in our previous videos, we have already done examples to find this interval of definition, and it's basically when there is a vertical asymptote or discontinuity in the solution. And for non-linear ones, it will be sometimes difficult since you don't know what restriction on the interval will be needed to find where this solution exists, but at least we know it does. And lastly, what I'd like to point out is a general solution. And basically, this is different because for a first order linear equation, it is possible to obtain a solution with only one constant. But for nonlinear, that may not be the case, even though a solution containing a constant, an arbitrary constant, can be found. There may be other solutions that cannot be obtained by this constant. So what do I mean? Well, we can solve the ODE dy dx equals to y to get like y equals to e x aex, and in this case now every solution is of the form of this, where they means they differ only by a multiplicative constant. But for a nonlinear equation, that may not be the case. So you might have some solution come out, and in that case, when you solve it, you actually realize that even with the constant there, it doesn't, different solutions might not be related to one another proportionately. So we can see that from the example where dy dx equals to y squared, and the expression contains a constant but does not include all the solutions. And that's because we observe that the function y equals to 0 is certainly a solution but cannot be obtained by any value when you assign the constant to. So we can see how non-linear and linear equations differ in this general solution aspect as well. So I've come to the end of this video. I hope you have enjoyed it. Please like, share and subscribe. Leave any comments for me to answer. Any questions, I will answer them. And I'll catch you in the next one. Bye.